Okay, in this video we're going to look at factorial, what it is, why we have it, how to evaluate it, and also look at the question why 0 factorial equals 1 instead of, say, 0. So we're going to start this off with a little example problem that will help us understand why we can use factorial, and the question is, in how many ways can we rearrange the letters A, B, and C? And if you have no better idea as to how to start, you can just start listing them. So you could do, let's say, ABC, same order, or you could do ACB. You could do BAC, BCA, or you could do CAB and CBA. And so you can see that there are 6 ways. In a little different way, to answer the same question, I could also work a little bit smarter, like the last lesson in counting. I could make a tree to see what's happening here. And so if I'm trying to rearrange these 3 letters, I have 3 choices for the first letter. It can either be A, it can be B, or it can be C. Once I've chosen the first letter as A, I don't have A from which to choose anymore, so I can only have B or C. So for each of these 3, there will be 2 choices, but the choices will change depending on which letter we chose. So if the first letter is A, then the second letter can either be B or can be C. If the first letter is B, then the second letter can either be A or C. If the first letter is C, then the second letter can either be A or B. And finally, once I've chosen the first 2 letters, then there's only one choice left. So if I chose A first and B second, the last thing has to be C there, no other choices. If I've chosen A first and C second, my last letter has to be B, and so forth and so on. B, A, C, B, C, A, C, A, B, and C, B, A. And so in here, we can see, let me change colors, that there are 1, 2, 3, 4, 5, 6 outcomes. The outcomes are the leaves of this tree, and each one of these includes all of the branches to get there. So for instance, this leaf here stands for the outcome C, A, B, because the way to get there is to first choose C, then choose A, then choose B. But here's where the problem comes in. This was 3 letters and we had 6 choices. What if we had 4 or 5, 100 letters or symbols from which to choose? There's got to be a better way. And this is where it leads into this next idea, in that instead of just sort of diving right in, I like to think of it this way. If I'm rearranging 3 letters, I really have 3 spaces to fill. This first space, I have 3 symbols or letters to choose from, so there are 3 choices there. When I've filled this up, then I only have 2 choices left over. And when I've filled both of these, I only have 1 choice left over. So in this case, like we saw last video, I have 3 choices, and then 2 choices, and then 1 choice. And so I can multiply through 3 times 2 times 1 gives me 6. And I can continue this process to get for larger and larger numbers. And this leads us right into factorial. So this factorial, notationally, we have for integers n, and we're only going to consider non-negative, where n is greater than or equal to 0. Factorial is written n and then an exclamation point. And there are a few ways I can define this. So one way to define it is to say that n factorial measures the number of ways to arrange. Let me say instead of arrange, let me say order. First, second, third, fourth, so forth and so on. N distinct objects or elements or whatever. So in our previous problem we had 3 distinct objects. There were 3 letters, and so 3 factorial gave me 6 ways to order them. That's one way to look at it. Another way to look at it is this. So for any n greater than or equal to 1, n factorial is the product of every integer from 1 to n. Now, in this case, I said multiplying from 1 up to n, but oftentimes I actually multiply the higher numbers first because I think it's a little bit easier. It doesn't really matter. Notice factorial deals with n greater than or equal to 0. This only deals with n greater than or equal to 1. If n is equal to 0, then n factorial is going to be 0 factorial, and that's going to be defined as 1. And we can talk about that a little bit already, but we'll look at it in the next slide. So why is this 0 factorial 1 instead of 0? Okay. Now, I can write this in a different way. I can use product notation. So we'll say 0 factorial is going to equal 1. And for n greater than or equal to 1, for integers n, we're going to only consider integers here, n factorial will equal the product, and this capital pi is like the capital sigma for sum, the product as k goes from 1 to n of k. So, an example here. So, what does this notation mean? This means that 3 factorial is going to be the product as k goes from 1 up to 3 of k. And just like with sum, we put in 1 first and multiply instead of add. Then we put in 2, then multiply and put in 3, and 3 is our stopping point, so we get that 6 again. And a final way to look at this would be to consider this recursively. So I could also say we'll define 0 factorial as 1, and for all n greater than or equal to 1, n factorial will equal n times n minus 1 factorial. And so this should make some sense. Let's consider something like 5 factorial. Little example here. So we know that 5 factorial is, it multiplies from this one, everything from 1 up to 5. So 5 times 4 times 3 times 2 times 1. And again, I like going this way because I find it easier to multiply at the end with these small numbers instead of multiplying at the end with the larger numbers. All this says here is that 5 factorial is going to be 5 times 4 factorial. 4 times 3 times 2 times 1 is 4 factorial. And this here, this idea will be very useful later on when we try to reduce rational expressions with, or fractional expressions with factorials in it. But now let's talk about this big issue. Why is 0 factorial 1? So, a few things. First off, on that last slide, we said that 0 factorial should measure the ways, or the number of ways, to order 0 elements or objects, distinct objects. If I have no objects, there's one way to order it, and that's just no objects. That is one thing. It's sort of it's the same idea as having like an empty set. There's one thing that has nothing in it, and that's the one way. Now, if you don't like that, this is what usually makes the most sense to my students, is we just sort of start talking about a pattern that makes sense. So, I want to know what 0 factorial is. And we aren't sure yet. Okay, I told you it's 1, but don't believe me. Make sure it makes sense. 1 factorial is just 1, because the product of every number from 1 to 1 is just 1. 2 factorial is going to be the product of everything from 1 to 2, so we have 2 times 1, which is 2. 3 factorial, 3 times 2 times 1, which is 6. 4 factorial, which is going to be 4 times 3 times 2 times 1, which is going to be 24. And I'll put one more up, 5 factorial, which is 5 times 4 times 3 times 2 times 1. And we can start using that last trick. 5 factorial is just 5 times 4 factorial. I knew this already was 24 from right here, so I just do 5 times 24, and I'll get 120. And we can keep on getting bigger and bigger, but what I'm going to do is figure out how I could get from one term up a level. So to get from 5 factorial to 4 factorial, we had to divide by 5. To get from 4 factorial to 3 factorial, we had to divide by 4. To get from 3 factorial to 2 factorial, we divide by 3. 2 factorial to 1 factorial, we divided by 2. And now, to get from 1 factorial to 0 factorial, we'll divide by 1. You can see the pattern. And 1 divided by 1 is 1. So, based on this pattern, you can clearly see, okay, it makes more sense to make this 1 than it does to make it 0 if we're following this pattern. The last thing I'm going to say about this is probably the most important thing. So, 0 factorial equaling 1 is crucially important to make later formulas simple. So, starting the next lesson, we'll see the formula for NPR, or the number of permutations. And if I allow 0 factorial to be 1, it's a really easy formula. You can just put it in, you get the answer. If I make 0 factorial 0, I'll end up dividing by 0, and that'd be very bad. So, one last thing before I move on from here. I just want to address how to get this to work in the calculator. So, factorial is going to be under this math symbol. And I can do something like we start off with 3 factorial, so 3, math, go over to PRB, and you see factorial is the 4th thing in the menu. 3 factorial gives me 6. And if you didn't believe me about 0 factorial, well, Texas Instruments believes 0 factorial should also be 1. You can see it right here. Okay. Alright, so let's look at another example. And here we have this one. In how many ways can you line up the 4 people, Abby, Betty, Charlie, and Danny? Well, this is pretty much the same problem we had from the beginning. It's just instead of having 3 elements, we have 4 elements. So you could consider, okay, you could either do all this work by saying, okay, there are 4 spots in my line, and for the first spot, it could be any one of those 4 people. For the second spot, it could be any one of the 3 remaining people that isn't in front. For the third spot, it could be any of the remaining people that are not in the front too. And then once I have the first 3 people filled in, the last spot only has one choice. And I'm choosing this and this and this and this, and usually becomes a multiplication problem. We get to 24. But since there are 4 distinct objects or elements here, I could have just done 4 factorial, which is equal to 24. All right, 2 more things. First off, what does n factorial look like when it's expanded? And this, I know that my Calculus BC students have to deal some with it. It's worth figuring out what's going on with this. So when I'm just considering n factorial, we know that that's going to be the product of every integer from 1 to n. So long as n is greater than or equal to 1, it's going to end up being n. And then we multiply that by 1 less than n. Multiply that by 2 less than n. And I can continue multiplying that all the way down to, I probably don't need that, 2 times 1. So what I mean by this is if I had some large number like 17 factorial, we know that I'm going to start off doing 17 times 17 minus 1, 16 times 17 minus 2, 15, and continue this process all the way down to 2 times 1. With this idea, I can actually do some work or some simplification nicely. So let me consider 2 problems here. First, I'll do a numerical problem, and then I'll do an algebraic problem. So numerically, let's consider 10 factorial divided by 7 factorial. And I'm going to do this one by hand. It's going to be actually pretty quick and easy. And once you catch the trick, these problems by hand are not that difficult. So I'll expand them all out so we can see what's happening. In the numerator, I have 10 times 9 times 8 times, and I'll write it all the way out, but you can actually save yourself some time when you catch the pattern. The denominator is just 7 times 6 times 5 times 4 times 3 times 2 times 1. And you can see already what's happening. Instead of doing all of this writing, I could have just written this as 10 times 9 times 8 times 7 factorial, using that sort of recursive definition. And we already had a 7 factorial down here, so that we have these 7, 6, 5, 4, 3, 2, and 1 cancel, so the 7 factorials canceled, such that when everything in this denominator cancels out, we're actually left with a 1 down there. When you cancel out things by division, it becomes a 1. And now I just need to do 10 times 9 times 8. And 10 times 9 is 90, times 8 is 720. Now another thing that can happen, so this is with numbers, and this type of work will be done quite a lot, but I could also do this with algebraic expressions. So I could have something like this. Let's do n plus 1. Actually, let's do it this way. N minus 1 factorial all over n plus 1 factorial. And here's the way I like to look at it. Same thing that happened here. We have 2 factorial, so there's going to be stuff canceling. We're going to have things left over on the larger side. So the larger of these 2 is the n plus 1. And it is 2 elements larger, because down here I'm going to end up having n plus 1 times, I decrease this by 1, n times decrease this by 1, n minus 1. I keep going, so I'll just leave that factorial there. And right here, n minus 1 factorial. So we can see that there were 2 extra elements here. This is the same thing as n minus 1 if I multiply it by n and n plus 1 to get those next 2 elements getting up there. Here the n minus 1s cancel out. I'm left with 1 over, and I can distribute this through, n squared plus n. Alright, next video, I'll go through some examples showing how this stuff works in various problems, very abstract, some applied as well.